Hello, this is Amber
and Yao from NYU Shanghai.
In this video, we will present our project about speech accent detection in our Machine Learning Spring 2019 class.
People's speech can usually reveal a lot of information, such as their ideas, emotions, gender, age, etc., also their origin. As English is becoming a worldwide speaking language, different English accent is common to be spotted in intercultural communications. The accents can reflect their linguistic backgrounds and the geographic origins. In our final project, we aim to implementing machine learning algorithms to detect the English accent of a person with respect to his or her native language. Here we focus more on detecting the accent of English native speakers due to the limitation of the data. There will be a wide range of applications of the project. For example, automatic interpretation system can be improved by providing a precise target language. Companies can build a better advertising and recommendation system. Also, individuals can identify groups with similar backgrounds and identities more easily with the help of the algorithm.
The dataset we use is the Speech Accent Archive obtained from Kaggle. The dataset contains speech samples of people with 200 different native languages, all reading the same passage in English.
Please call Stella. Ask her to bring this thing with her from the store. 6 spoons of fresh snow peas, 5 thick slabs of blue cheese, and maybe a snake for her brother Bob.
Please call Stella. Ask her to bring these things with her from the store. 6 spoons of fresh snow peas, 5 thick slabs of blue cheese, and maybe a snack for her brother Bob.
In total, there are 2,138 speech audios. Each sample has a label indicating the native language of the speaker. Among the speakers, 3/4 of them are non-English native speakers, and 1/4 of them are English native speakers. In order to deal with the unbalanced data, we use random oversampling to increase the number of English native samples to be the same as non-English native samples. Therefore, we have total 3,118 data points. We further split them to train, validation, and test sets. Let's first go through the models we use. Long short-term memory networks, also known as LSTM networks, is a special kind of RNN capable of learning long-term dependencies. It is particularly useful for sequence data such as speech or action recognition. A common LSTM unit is composed of 4 interacting layers. The first is a sigmoid layer called forget gate. It decides what information should be thrown away from the cell. The next is the input gate layer to decide what new information should be stored in the cell. The key differences of LSTM compared to standard RNN is the cell state, which allows information to flow along it unchanged. In this layer, it drops the information decided to forget and then update the new information. The last is the output gate deciding the output information. The methodology of the project is as follows. For each speech sample, we first trim or pad a 10-second clip to fix the length of the sequence data. We then use the LibreSol library to extract its male frequency capture coefficient MFCC features. We keep the only first 13 features because they represent the frequencies most relevant to human voice. By tweaking the sampling rate, for each data point, we result in a 500 by 13 2D MCC array, which could be used to feed into our model. Each row represents a time frame with a fixed size of 13 features. It becomes the input X along the sequence model. Both LSTM and RNN we used are many-to-one sequence models. They run through a softmax layer in the end to output the predicted probabilities of native and non-native classification.
After converting the raw audio into MFCC, we pre-process the data further. We firstly oversample the data randomly to make sure the numbers of the input of the two classes are the same, as described above. In addition, we also tried some scaling methods such as normalizing the length and applying min-max scalar, but we discovered that these scaling methods do not help the classification since they decrease the influence of some extreme values, which carry some important information by themselves. These are the models we built. For the hyperparameters, we tried hidden size of 32, 128, 256, learning rate of 0.0001, 0.001, and 0.005, iterations of 5 and 10, number of layers of 1 and 2. And here presents the set of hyperparameters which produce the best performance. Those are the training and the validation performance of our models. As we can see from the graphs, LSTM produced a better result than RNN by having a clear trend of loss decrease and higher accuracy. The accuracy on the testing dataset also proved that LSTM is a better model in this task. It can classify 65% of the audio input right, and it detects 70.16% of the accent of native English speakers. If we have more time, we will try other more advanced algorithms to further improve the results. The dataset here does not have adequate data for English accents other than native English speakers. We would like to help build a better database so that we can apply our model to classify other English accents and detect the origins of the speakers. Other than those, we also want to adjust the model to detect more information other than accents, such as gender, age, etc., to widen the application of our system.
Here are the sources and references we used for our project. We would like to give special thanks to Professor Keith Ross and our teaching assistant Autumn Wu and Watcher Wang for their support and guidance. Thank you so much for watching. Thank you.